welcome back. We are discussing about limit of a function at a point, and then what we have seen is that we, in order to define the limit, let us say f of x goes to a, then we are looking, suppose if your a is here, then we are considering the properties of f in this neighborhood a minus delta to a plus delta for some delta positive. Now, suppose we have a function, let us say f, which is defined from closed interval a b to, let us say, r. Now, if we are interested, then what are the nearby values of f at a and limit x goes to a. In this case, you see, or x goes to b for that matter. In this case, we cannot, this a minus delta and a plus delta we want to see, this is not in the domain of a. If this is not the domain of a, then we have only information about f from all such x which are greater than a. Similarly, this kind of thing can happen at the end point, where b minus delta to, let us say, b plus delta, then we do not have any information, because our f is not defined on b to b plus delta. So, how to address this problem? So, in that way we define something called a one sided limit. Now, what is that? For example, if I take this is what precisely what we discussed. If we take a set A to be closed interval 0 1. So, as x approaches to 0 from the left, that means 0 is here. So, then chi of A, suppose it is approaching from here, then you see all these values, f chi of A is taking the value 0. So, and but however, if I want to approach it from the right hand side, then this is the function, suppose 0 1, this is 0, this is 1, then our function is 1 here and 0 here and 0 here. If you approach to 0 from the left, you will get the limit to be 0. If you approach the 0 from the right, then what you are going to get is that the limit to be 1. So, there is no single number, one can see that. So, you cannot find a single number for which chi of a approaches to that number when x approaches to 0, because if you approach from left hand side, you are going to get 0. If you are approaching right hand side, then you are going to get 1. And we have already seen that if limit exists, then it has to be a unique number. So, there is not a single number in which we can talk about the limit. So, this we can, this phenomena we can indicate it as in the symbol as the limit x goes to 0 minus, which means you are approaching to 0 from the left hand side of the 0, and limit x goes to 0 plus, which means you are approaching 0 from the right hand side of 0. So, now for the symbol limit x goes to a minus, we consider only the values of x that are less than a. Similarly, for limit x goes to a plus, means we are considering the values of x which are greater than a. So, now we define limit x goes to a minus f of x is equal to L. That means, the left hand side, left hand limit of f of x as x approaches to a from the left is equal to L. If we make the value of f of x arbitrarily close to L, that is the concept of limit, that f of x should be arbitrarily close to L, it should be as close as we want, but when x is close to a is the limit, here the taking sufficiently close to a, and not only that, we have to get that x has to be less than a. That means, you are approaching from the left. So, for example, here if you look at here, then this is your a, then for x approaches to a minus, will that means, this is what it is, the red line will indicate that x approaches to a minus, that is from the left. So, this is the left hand limit, we can define the right hand limit in the same fashion. So, when f of limit x goes to a plus, f of x is equal to L, that means, if we take the values of f of x when close to a from the right hand side, and that means, f of x is greater than a, then we talk about the right hand limit. So, the theorem it says that if limit exists, limit of f of x is equal to L, if and only if both left hand limit exist and it is equal to L, and the right hand limit exists and it is equal to L. So, both the limit will exist and they will take the same value, then we say that limit f of x goes to a is equal to L. Now, let us see this function. So, which is defined, f of x is taking the value of 1 and at half 0, then it is taking the value 1 on the interval 0 to 3. So, which means f of x is equal to 1 when x belongs to half open 3 open, and then f of 3 we are defining, let us say some value, let us say 2, and then this. Then now look at the points. So, if we look at a is to be half, then when I am traveling from the left, we are approaching to 0, right, and when a is half, when we are traveling from the right, all these values are constant 1. So, this is 1. Therefore, the limit at f of x goes to half does not exist. In order to limit exist, limit of f of x goes to a has a plus is equal to limit f of x goes to a minus, left hand limit and right hand limit should match. So, the limit is not going to exist at 1/2. Also, if you look at 3, so at this point, if I am approaching from this side, all the values, this is taking 1. So, from the left hand limit, it is going to be equal to 1, and from the right hand side, if I come, so this is going to be closer to 1, all this. So, now right hand limit is also going to be 1. How? So, therefore, here in this case, limit f of x goes to 3, it exists, and which is equal to 1, because left hand limit and right hand limit are equal to 1. However, in this case, what we find that this is not equal to f of 3, f of 3 is 2, that is what we had defined. So, here is the question, there are two issues. One is the limit exists, means the left hand limit and right hand limit will should exist and they must be equal. It is not necessarily true that the limit of f of x goes to a is going to be equal to f of a. That may not be true, because f of a can be defined in a different way. So, here till this point we have considered a to be a real number, and the limit we have considered again L, f of x goes to a is going to be a real number. So, now it can happen, suppose look at f of x equal to x. So, whenever you go for large x, your f of x is going to be larger and larger. So, that means it is going towards infinity. So, this we can say that we denote it that limit f of x, x goes to a is equal to infinity. That means what? That means, you see, infinity means what? Which means if I give you some positive number, you can always find in the neighborhood of a, you will find some x in that neighborhood which in which f of x will be bigger than the large number. So, that is what, if we want to write it down, then one say that can the value of f of x can be made arbitrarily large by taking x sufficiently close to a, but not equal to a. So, in the sense that in other words, suppose m is positive, for any given m there exists a delta greater than 0 such that x belongs to, if x belongs to a minus delta, a plus delta, except possibly a, will imply that f of x is greater than m. That is what the arbitrarily large means. Sometimes we write that f of x converges to infinity as x goes to a. Similarly, we can define for the large negative. It can, f of x can go to minus of infinity as x goes to a. So, here is one example. I am taking f of x equal to 1 upon x square, as this is the what the graph is going to be. Now, you can see that suppose if you fix your m, then this is your delta, which is going to give you, this is minus delta to delta, in which f of x, in this f of x is going to be bigger than this m. Wherever you fix your m, suppose your m is somewhere here, whatever the large. So, you can go up to this. So, now beyond this, so in this interval definitely this is going to be bigger than the m what we have chosen. So, this is what we can write it as that limit of f of 1 by x square, x goes to 0, this is equal to infinity. So, as we had said earlier, we have seen that the limit of f of x, x goes to a may exist, but it may not be equal to f of a. So, and let us look at these two functions. Here is one f of x equal to x, which is a uniform. As per the weight, suppose I will say that whatever your weight and you pay that much of amount for your parcel. Now, here is something called a post office function. Suppose for the weight of 0 to 5 we pay 10 rupees, and 5 to 10 we pay 12 rupees, and 10 to 15 gram we pay 14 rupees. Now, so this is what it is saying. Suppose if you in this case in figure 2 f of 4.9, suppose you have a 4.9, here in this case it will be f of x 4.9 will be 4.9, but in this case f of 4.9 is going to be 10, because this is 4.9 would be less than 5. However, f of 5.1 this is going to be 12, f of 5.01 is also going to be 12. So, anything f of 5 plus delta, delta positive, that is, and which is less than 5 of course, which is going to give you 12. So, there is a certain jump. So, let us catch this phenomena. So, we call it a function f to be continuous at a if limit of f of x, x goes to a is equal to f of a. So, okay, let us see what are the assumptions we are making while we are saying this, that f of a is defined. for example, f of x equal to 1 over x. So, f of 0 is not defined, but here in order to assume to say that f is continuous at a, f has to be defined at a, and limit of x goes to a f of x is equal to f of a. That means, what we are saying is that limit f of x, x goes to a exists. That means, what it is saying that in order to this to exist, f has to be defined in some neighborhood of a, and now f of a is defined. So, now it is defined on the entire neighborhood of a minus epsilon to a plus epsilon. And then finally, what we are saying, you have all the thing f is defined in this neighborhood, and you can calculate the limit, find the limit, whatever the limit, if that is equal to f of a or not, f of a is also defined. Remember that in order to define limit, what we have said is that f may be defined in the neighborhood of a except possibly at a. To get the limit f of x, x goes to a, we do not need the value of f at a, but for continuity f of a has to be defined and limit of f of x, x goes to a must be equal to f of a. Okay, so, now let us try to look at few concrete example. So, we define f of x equal to x square minus 2 x minus 3 by x minus 3. So, now here you can see that f is not defined at x equal to 3, because denominator is going to be 0. So, safely you can say that f is not continuous at x equal to 3. Now, the same function, if I define f of x equal to x square minus 2 x minus 3 by x minus 3 if x is not equal to 3, and I give the value 2 if x is equal to 3. Now, f of 3 is defined. Now, to check the continuity at 3, we need to find limit f of x, x goes to 3, we need to calculate that, and that must be equal to 2. If that happens, then we can say that f is continuous at 3. So, f of 3 is, now let us calculate limit, left hand limit and the right hand limit. If I calculate the left hand limit, in order to say that limit exists, we need to calculate left hand limit and right hand limit. So, f of x equal to x square minus 2 x minus 3 by x minus 3. Now, remember that in order to calculate the limit, what we are saying is that this x may not be equal to 3, we do not need that condition. So, x minus 3 for any x, here in this case x is not equal to 3 and the x is less than 3. So, x minus 3 is not equal to 0 for those x. So, this we can factorize, and then what we are going to get, this is nothing but x plus 4, because this and this gets cancelled. So, limit x goes to 3 minus x plus 1 is equal to 4. Similarly, we can find the right hand limit, which is also going to be equal to 4, because the same phenomena x minus 3 is not equal to 0. So, we can cancel at the numerator and the denominator, and so the limit, right hand limit will also be equal to 4. So, limit x goes to 3 f of x is nothing but equal to 4. However, this is not equal to f of 3. Thus, f is discontinuous at x equal to 3. Now, if we change the function little bit, f of x is equal to x square minus 2 x minus 3 by x minus 3 when x is not equal to 3, and 4 is equal to, if x is equal to 3, what we have seen from the above, that the limit f of x, x goes to 3 is equal to 4, which would be f of 3. So, in this case we will say that this function is continuous at x equal to 3, whereas this and this, they are not continuous at x equal to 3. Now, let us consider the function f of x equal to 1 when x equal to closed interval belongs to closed interval 0 1 and 0 otherwise. Now, we have discussed this earlier. If I am taking limit, this is defined on the 0 and 1. So, only limit if I am going to 1 from the left hand side, this is the function. So, this is going to be 1. If I approach 1 on this side, then I am going to get 0, because all these values of f of x is equal to 0. And similarly, in this example, if I look at 0, then if I approach 0 from the right, then I am going to get 1, and approach 0 from the left, you are going to get 0. So, this also suggests that, well, I mean, we have a concept of one sided limit, then it, suppose at the end point what happens about the continuity, because we do not have, suppose our function f is defined to from a b to r. Certainly, we cannot talk about the continuity of f at the point a. In order to do that, our f must be defined on a minus delta to a plus delta, but it is not defined here, but it is defined from a to a plus delta. So, like the right hand limit, or in this case the left hand limit, we can talk of the right hand and left hand limit. So, in that case what happens to the continuity? So, this is one sided continuity. So, we will say that f is continuous from the left at a if you approach from the left hand side limit, then left hand limit is equal to f of a, and f is continuous from right if approach from the you take the right hand limit of f of x, x goes to a plus. If that is equal to f of a, then we say that f is continuous at a from right. So, for example, the previous example what we had seen, this is the indicator function of 0 1 close 0, f is continuous from the right at 0, because on the right hand side f of 0, as you can see, this is equal to 1. Therefore, if you approach the 0 from the right hand side, you are going to get the limit 1, and if you approach from the left, you are going to get the limit to be 0. So, here the right hand limit is equal to 1, which is equal to f of 0. So, therefore, f is continuous from right at 0. Similarly, f is continuous from left at 1, because from the left you go, you are going to get 1, and that is equal to f of 1, because f is 1 on the closed interval 0 1. So, this f is not continuous at 1 or at 0, but it is continuous from right at 0 and continuous from left at 1. Now, this we can extend, we can apply this concept of left continuity and right continuity for any functions which are defined on the closed interval, closed and bounded interval a b at the end point of these intervals. So, naturally, in the left end point we can only talk about the right hand limit. So, therefore, it only possibility is that it can be right continuous or it may not be right continuous. On the right end point, we can only approach the right end point from inside, that means from the left. Therefore, the only possibility at the right end point is that it can be at most left continuous. So, now for concrete example, let us consider f of x is the square root of 1 minus x square. So, at minus 1 and at 1, this is going to be f of minus 1 is equal to 0 and f of 1 is equal to 0. Now, if x is bigger than 1, then this quantity 1 minus x square is negative. Therefore, square root is not defined. So, f is not defined outside 1. Similarly, if x is less than minus 1, then x square is going to be greater than 1. Therefore, this quantity is going to be a negative number. We cannot define the square root. However, if my x is in minus 1 1 in this open interval, then f of a is the square root of 1 minus a square. Now, if I take limit x tends to a is not on minus 1 and 1, however close it can be, but we can always get a delta such that a minus delta is bigger than minus 1 or a plus delta is less than 1. Therefore, we do not have any problem in defining this, and so limit which would be equal to the limit f of x goes to a. Therefore, for all those point a lying between open interval minus 1 to 1, f is continuous. Now, at the end point, what we can see is the minus 1, I can only talk of the limit from the right. So, minus 1 plus, which is equal to limit of square root of 1 minus of x square, it is missing, which is 0, which is equal to f of minus 1. And similarly, if I try it from the 1, then if this is 1, then we can talk of the left hand limit, and there it is going to be 0, which is again f of 1. So, f is continuous from the right at x equal to minus 1 and continuous from the left at x is equal to 1. So, now with the continuity like in the limit, let us be more formal and give an epsilon delta definition. So, limit we know that we have said that at f is continuous at a if limit of f of x goes to a is equal to f of a. So, that means this is what is our L. So, we know the definition of the limit in terms of the epsilon and delta. So, we say that f is continuous at a if for any given epsilon positive there exists a delta greater than 0, such that mod of f of x minus of f of a is less than epsilon whenever mod x minus of a is less than delta. That is what is then the proper definition of the continuity of f at a. Okay. So, this is just the L, this is we are not doing anything other than that this is the L, we have studied this definition, and here the L has to be f of a, that is what it is. Thank you for your patience.